I am just going to give just one or two examples on some of the uses and applications of pattern recognition. This thing I should have told in the very first lecture, which I did not include, which I observed that I did not say this thing. So, I am telling it now. This is the example that I really like this example. It is crossing the road. Crossing the road. So, suppose you and your friend, you have gone out and there is a road in front of your IIT. Okay. You would like to cross the road to the other side. Now, my question to you is it necessarily true that you will cross the road at the same time? No. Though you went there at the same time, probably on the other side one of you has some work, other one is accompanying, okay. And so relaxedly you are trying to cross the road, and one person may cross first, another person may cross later. Now, my question to you is, for the same situation and exactly everything is same, your output is different. If you look at it from the point of view of you need to make a judgment, or you need to make a decision. Everything is same, but the judgments are different. The decisions are different. Do you think one of you is right and the other one is wrong? No. Both of you are equally right. This is an example where exactly for the same situation, in every respect everything is same, but you have two equally good answers. You have two equally good answers. Now, let me tell you some things regarding this. When you are making the decision, note that your information that is given to you, one car is coming from on the other side, you have looked at it, maybe 2 or 3 cars. Do you know the speed of the car exactly? No. Note that a person who never drove a car or who never drove a vehicle can cross the road. A person who has driven a vehicle, probably he or she has some idea about the speed of the vehicle, but even if a person has not driven any vehicle whatsoever, he or she can cross the road. An illiterate person can cross the road. A child of age 7 or 8 years can cross the road. Now, you want to write a program for crossing the road. How do you write it? The input to this is not precise. Is the input precise? No. The input is not precise, and in fact, is your logic precise? No. Even then you are able to cross the road. This is a nice example to say that many times human beings have imprecise, imperfect and imprecise, imperfect, ambiguous information, and from there we make judgments and we go ahead. One of the aims of pattern recognition is to model this imprecision, ambiguity, and to make a system so that the system works. Note that the decision, the output need not be unique. If you need unique output, that is fine, but many times we do not need unique output. This is one example that I wanted to tell you, and there is another example. This is a chalk piece, right. Many times in our childhood, in my childhood at least, what I tried to do was, I tried to balance this in my hand. I hope many of you have done it when you were a child and probably failed. Okay. This problem of balancing any object like this, there is a name for it. This is inverted pendulum problem. A pendulum, you know, there is a thread and then there is a small bob attached towards the end of the thread. Now, that is pendulum, and then you invert it. That means, the thread portion, instead of thread you put a stick, it comes like this and the blob is up. The stick is like this, the blob is up, that is inverted pendulum. This you need to balance it. You would like to write a program for balancing it. What is the meaning of writing a program? If it is falling in this direction, then you need to somehow estimate the speed at which it is falling and the angle at which it is falling, and somehow you need to change your hand, you need to probably bend the hand or at the same speed or maybe slightly more speed. You need to do all these things for writing a program for this. Now, you may ask me a question, why balancing a stick is a problem? Why does one need to do it? What is the use of this solving this problem? The use, I will tell you one or two uses. From this probably you will be able to get many other uses. Suppose you would like to make an unmanned aircraft, so that this aircraft would fly into enemy territory to find out what the enemies are doing. Enemy territory or the nearby country territory, whatever it is, you would like to send an unmanned aircraft. Why unmanned aircraft? If you send a human being inside the aircraft, since it is done illegally, you have not taken any permission from the other place to fly into it, they may as well shoot this aircraft, so that the person may die, and that will become a scandal. So, you would like to have an unmanned aircraft here, so that even then someone shoots this one, no problem, only machine is getting wasted, some money is going into the drain, but human beings' lives are not lost. So, you would like to have an unmanned aircraft to fly into some unknown territory. So, unmanned aircraft means how does it navigate? Again you need to have some sensors, and then the sensor is going to get the input and some decisions are to be made. Note that many of these decisions which must be taken, they are to be taken very fast, because the object is moving, the aircraft is moving, it is not standing still. Aircraft is moving, suddenly it sensed something there, okay. Then immediately it needs to change the direction. There something it has seen, immediately it needs to change the direction. That is very similar to, this is falling, you need to change it. Again something is happening, you need to change it. Have you understood what I wanted to say? If you solve this problem, then the similar logic you can apply to solve the problem of having an unmanned aircraft. I mean, how do you actually collecting the information is one part, analysis and interpretation, and you need to have actually an online algorithm for doing this thing. So, that problem is very much similar to it. This is about aircraft. Similarly, you may want to have unmanned trains. Anyway, unmanned trains are there in the world. Train is moving and then there is a signal, it needs to stop, and there is a bend. There also the information, how much bend is there. You see, you may not have the exact value. Similarly, when you are taking a photograph from such a distance to the earth from low flying aircraft, you may not have the exact information. There is ambiguity present, but you need to write your rules based on those ambiguities. If you have something precise, it is fine, but you cannot guarantee that everything that you are able to sense is precise, or I mean you cannot guarantee that, and you need to work on these imprecise things. So, you need to, in order to make all these systems, you need to have the corresponding logic which deals with these ambiguities. It is very easy to say that you need to have logic which deals with these ambiguities, that is very easy to say, but I do not think till now we really have the complete logic. Partially at some places, yes, we have it, and note that the moment there is an ambiguity and the moment we make decisions on the basis of this ambiguity, sometimes our decisions can go wrong. It is not necessarily true that every time the decisions are right. Then there is a very basic question. The very basic question is, if you want to ensure that no decision would be wrong, then can you do it? And if you cannot do it, that means you are able to, you are saying that some decisions can go wrong, then how much percentage? And once you decide the percentage, do you have the corresponding logic automatically? See, these are all very big questions for which till now there are no answers. Till now there are no good answers, and I mentioned in one of the first lectures, first few lectures, 1 or 2 lectures, I do not remember, compared to the aim of what we want to achieve in pattern recognition, what we have achieved is only epsilon. Compared to what we wanted to achieve, what we have achieved till now is only epsilon, and in that epsilon we will be teaching epsilon here. In that epsilon we will be teaching epsilon here. I think that is it. Given a data set, how do we know that we need to do clustering? This question can be put in many ways. Suppose your data set is say like this. Then actually there are no clusters here. In fact, suppose say this is say A minimum, say the maximum is say B here, and then this is A1, this is A2, and say here it is say B1, and then the highest is say B2. One can say it is uniformly distributed data, x it is A1 A2 and y it is B1 B2. So, when you have uniform distribution, you cannot have any clustering. So, the first question is, if you are given a data set before you want to apply any clustering algorithm, what you need to first find out is whether the data has clusters. One way of putting it is that check whether the data follows uniform distribution. If the data follows uniform distribution, then there are no clusters. How do you know whether the data follows uniform distribution or not? For this you need to refer to Dupes and Jane's book on algorithms for clustering data, where they discussed all these tests, whether the data follows uniform distribution or not. How do you judge it? Those tests are given there. Now, so the first one is that the data should have at least one cluster. What is the meaning of the data having one cluster? Suppose the data is say unimodal data, mode is only one, say something like this. Single dimensional data, this point occurs maximum number of times and then slowly and slowly the number of occurrences decrease. Then you have a single mode here, that means you have only one cluster. If you have only one cluster, you do not need to do any clustering. You look at the terminology, here I said that there are no clusters, because somehow the points are occurring equally likely, and here some points are occurring more times and then some points are occurring less number of times. I am using the word you have only one cluster. I am differentiating this situation from this, and the next thing is that you should have more than one cluster. Okay, you should have more than one cluster. So, basically if the whole data follows uniform distribution, you cannot have, you need not have to apply any clustering algorithm, that is one. And secondly, if your data has exactly one mode or the data is unimodal, then you need not have to apply any clustering method. Only when the data is not following uniform distribution, a case like this, okay, the data is distributed in this way. If you look at each one, there is uniform here and on this one there is uniform, but if you put these two things together, then it is not following uniform distribution in this whole space, because there are many blanks here. Okay. So, if the data is not following uniform distribution, or if the data is not, if it has at least two modes, then you need to do clustering. Over. Questions? You do not know what to ask, fine. I will just say one thing, for many of these things the corresponding tests are given in Dupes and Jane's book, algorithms for clustering data. All the statistical tests you will find there.